Hi, I'm Sophia. I'm a PhD student from the University of Chicago. And as you can see, this is another talk on surface code. But I'll be talking about a different type of errors that's different from the erasure errors or incoherent errors that was on. The slide wasn't moving somehow. Yeah. Hopefully it will not disappear again. Yeah. So previous days people have been talking about erasure errors and incoherent errors and other errors, but today I'm going to talk about fabrication errors. So you may not have seen many people who write papers about the broken qubits on their devices because they have no incentive to do it unless they find out a way to reduce the defect rate. But they do exist, especially on superconducting qubits. One of the reasons is unlike neutral atoms, which just exist in nature and you just have to control them, superconducting qubits are designed and fabricated from scratch in layers. And right now, at least some of the steps are actually done by hand. So, and the Josephson junction and superconducting qubits are so tiny. So like naturally, there's going to be some variation and errors that you can expect in the fabrication process. So in this talk, I will refer to fabrication errors sometimes as defects, which is different from the defect that we usually talk about in quantum error correction. And defects can come in many different forms. Sometimes it could just be a broken wire or a piece of dust that you can just visually inspect by some standard microscopy techniques. Another concrete example is frequency collision on fixed frequency transmon devices. And here is a table of the frequency collisions. This is because fixed transmons are weakly anharmonic. So if the frequencies of nearby transmons are not what you want them to be, then sometimes when you're trying to control one gate, it could affect the neighboring gates, and it's going to be pretty disastrous. And so this table is stolen from a paper that introduces the so-called laser annealing technique that can reduce the variation in the qubit frequency so that frequency collision occurs less frequently, but still, they still happen. Like IBM is a company that uses fixed frequency transmons to build their device. So if you log into your IBM Quantum account and look at the device plots and see the errors, you can expect to see some qubits and links that are just that have from 10% up to 100% error rate, as it shows. But our project is not really restricted to fixed frequency transmons. It's for defects in general, not just, I would say we focus on static defects from fabrication errors, but actually if you have a qubit or a link that's lost for maybe a few hours or a few days due to, for example, TLS effects, you could also sort of count it as a static defect for the program that you're running. Let's shift topic to another element in my title, modular chiplets. So modular chiplet architecture is something that's pretty standard in classical computer architecture when they make those CPUs. And the idea is very simple. For the same number of defective physical qubits that you have, if you are working with smaller chiplets and only combining them to make a larger chip, then you don't have to throw away as many good qubits. So this flexibility of the modular architecture could help us improve the defect-free yield if we want to make a larger chip. Like one of the previous works from our group studied that. Although, I mean, the idea might sound very simple and intuitive, but like for that paper, they did a whole bunch of device modeling and analysis because there's some sort of trade-off that comes with decreasing the triplet size because the interchip links are like not expected to be as good as the on-chip links. So there's some trade-off that they analyze. Although some people very optimistically expect the interchip links to be eventually as good as the on-chip links. I'm not sure about like how much I should trust that claim, but like yeah, but that claim is not too relevant for our work, because in this work, we mostly focus on just placing a whole logical qubit on one chiplet, so we don't need to worry about like, the assumption that we made about the interchip links. So the thing is, even with the modular triplet architecture, the defect-free yield, which means like the proportion of triplets that don't have any defects on them, that's still too low. So naturally, we want to improve the results by using some of the defective triplets. But then the question is, which ones should we use? Well, I think one way to do it is just to pick the ones that have fewer defects on them. But that sounds a little bit naive, and there are many reasons why you may expect that might not be the best option, because maybe the locations of those defects also matter. So we chose, and to answer that question, we need to choose a target application. For that, we choose the rotated surface code. Part of the reason is because people are shifting towards fault-tolerant quantum computing these days. And another good thing about these codes is that while other algorithms might have a different structure on different places of the device, if you just want to implement topological codes, you basically have the same sort of circuits on everywhere. So it's pretty convenient. So after so many surface code talks, people may not want to see another intro to this. So I will just talk about the notation that I use. I use the red color for the X stabilizers and the Z stabilizers, the blue color for the Z stabilizers. Yeah, so one technique that our project builds upon is this thing called super stabilizers. So given an array of physical qubits that contains defects, how do we adapt or surface code to it? So one way to do it is to just create a large stabilizer around the defect, or in this case, a cluster of defects. We essentially can use the values of the broken stabilizers around the defect, and we treat them as a bigger stabilizer, and we just take the product of them and get knowledge of what's going on around the defect. And these are so the Z and X gauges around the defects, they don't commute, so they do have to be measured in alternate rounds. And let me go through these two examples. So on the top, I'm showing a broken data qubit, and as the result, the new X stabilizer around it is the product of these two red triangles, and the new Z stabilizer is the product of the two blue triangles. And then as the result, the code distance decreases by 1, because imagine that you want to cross from the blue edge from the top to the one from the bottom, you now get to skip the broken data qubit. And on the bottom, I call that as a defect cluster at the beginning, but it's actually a missing syndrome qubit. So when we have a missing syndrome qubit, this technique will require us to not only not use that, but also disable the 4 data qubits around it. So it's essentially a defect cluster. But the treatment for this defect cluster is still similar. You just take the product of even more gauge operators and use that as a big stabilizer. So we still have just one X stabilizer and one Z stabilizer around this defect cluster. In this case, the code distance drops by 2 because you get to skip this and this when you go like in the vertical direction, and you also get to skip 2 data qubits when you go horizontally. So, and then there was a follow-up paper that introduces these shells around defect clusters. So the problem with those higher weight stabilizers is that you have more measurement errors. So the values that you get are not as reliable. So one way to mitigate this is to instead of alternating between X and Z rounds immediately, you do the X round, for example, 3 times before you switch to doing the Z gauges, so that you can like get more information on the measurements. So with this technique, they achieved an analytic proof of a threshold. By which I mean, like, given a lattice with a fixed rate of random defect distribution, you expect that you can still get better performance by like just enlarging the patch of the code to include more physical qubits. Yeah, but like they didn't do any like experiments or anything. It was just an analytic proof. So before I continue to like the main question that we try to answer, let's do a sanity check. Like, because one of my lab mates, when I was starting to do this project, they were asking me, like, can't you just include a broken qubit as part of your code and pretend that it's not broken, because you have so many physical qubits that encode your logical information. Maybe one of them being broken wouldn't affect it as much. Well, if you only perform the memory experiment to like evaluate the harm of a broken qubit, this is actually what you will see, because the memory experiment doesn't really check for logical error strings that go in the time dimension. So yeah, like even if like you assume that one of your data or syndrome qubit is just spitting out some random outcome every round, you still only see a very, very small effect on the logical error rate, as if your code distance decreases by 1. However, like when you think about logical operations where you essentially have to change the definition of your logical operator. For example, when we do a merge in lattice surgery, we have to like, yeah, essentially move the logical operators like across the edge that we are merging. So in that case, you actually need reliable information about like every stabilizers. You can't really afford to have one like standard defect in this. And this can be captured by the stability experiment that's introduced by Craig Gidney. If you don't want to do a full simulation of a lattice surgery, yeah. So this is a plot that we made after running some stability experiment, and we compared a superstabilizer approach to the naive alternative of just keeping the bad qubit. And the setup that we have is just a defective data qubit at the center of a distance 5 rotated surface code patch. And you can see that like depending on the physical error rate, like when the broken qubit has error rate that's greater than around 5% or 8%, then we found that it's better to just disable it. So yeah, that's the sanity check. But in practice, well, another takeaway from this sanity check is that we sort of get a sense of what's the standard for labeling a qubit defective. Yeah, so actually the main question that we want to try to answer is which defective chips can be useful. And in other words, this is to say, if we want to build a modular device using chiplets, what's going to be the post-selection criteria that we use to select the chips? To answer this question, we need to identify indicators that characterize the performance of the surface code when it's adapted to defective arrays. And with this knowledge, we can evaluate another thing, which is the resource overhead that's caused by fabrication errors. By resource overhead, I mean like the total number of physical qubits that you expect to fabricate. And we can also try to evaluate how this depends on various design choices. But in order to achieve these goals, we first need an automated protocol to adapt the code, because we want to, because we need to sample a large number of random defect distributions, and we don't want to adapt the surface code by hand to all of these. Yeah, so this is the tool that we need in order to continue the study. So I just went ahead and made a protocol for that can adapt the rotated surface code to arbitrary defect distribution. And the process of coding this app was actually mostly I finished the code, thought it was good, and then I just tested on a bunch of random defect distributions, and then somehow it fails on one of them, and then I look into them and go back to modify the code until it just doesn't fail anymore. But in hindsight, there are actually just two things that needs to be taken care of. Well, actually, let me step back. So there are two steps in this protocol. One is deforming the boundary, because when you have a defective qubit or a link that's too close to the boundary, you actually cannot wrap it up with the superstabilizer, so you have to carve the defective links or qubit out of your code. So that's why we have these irregular boundaries. And the next step is, of course, to handle the interior defects, and that's easy. You just follow what's introduced in prior slides. And the thing about the boundary of rotated surface code is that they're actually pretty complicated, unlike the unrotated surface code. So they need a little bit of care. Here I'm showing some examples of how we need to do this. For example, in this case, we have a broken data qubit on the edge, and that's very easy. You just need to disable 2 qubits. However, if you have a broken syndrome qubit, then you have to carve out a larger chunk. And in this case, we have a broken Z syndrome on along a red boundary. So we need to carve out 4 physical qubits in total. However, on the other side, on the left edge of that other example, you have a broken red syndrome that's on a red boundary. So unfortunately, you have to carve out a lot more physical qubits because you want to maintain the color of the red boundary. And then on the lower edge on that side, I'm showing an example in which we have 2 broken qubits. And the one on the top, if you don't consider the other one, if you just consider the one on the top, then actually we could wrap it around with super stabilizer. But after you change the boundary due to the one that's on the very bottom, then we can no longer wrap it with a super stabilizer. So we need to further deform the boundary. So that's why I say that we need to go back and forth between these 2 steps. We need to deform the boundary and then try handling the interior defects. Sometimes handling the interior defects will require you to disable more qubits. For example, when you have a syndrome defect, and then more qubits might be too close to the boundary, so you have to go back to deforming the boundary. Yeah, so we just end up going back and forth between the 2 steps until we find that all the interior defects are actually interior defects, and they don't create more defects that are too close to the boundary. Yeah, so that's this protocol. It's quite messy. But I figured that I should just tell you a bit about it since I spent so much time writing it. So then we can try to identify the indicators for the performance of those defective patches. And actually, one of the prior work does have some numerical results, but so what they found is that the performance of a defective patch is worse than a defect-free patch with the same code distance. You might find this to be very natural, but let me emphasize that the code distance of a defective patch is actually smaller than the width of the lattice that you use to encode it. So in this figure, which is from their paper, so they are allocating, they're sampling defect distributions on a lattice with width 13, and then they're taking the defective patches that have code distance 9 and comparing it with the defect-free patches that are supported on with 9 lattices, and they got this result. So after seeing their paper, we thought that, well, maybe code distance wouldn't be a good indicator, and let's try to find other indicators. But also keep in mind that there are some limitations of their study. I don't mean to attack them, but their paper was from 2017, so at that time, there wasn't STEAM, there wasn't pi matching 2.0, so they actually couldn't run that many shots of experiments, so they only got results that are good for the regime that's for physical errors above 0.3%. However, we feel that studying what's going on below that error regime might be more useful, because that's closer to the regime that we expect that error correction will be useful for. And also, they were working with unrotated surface code. So now we feel that we should work on the rotated surface code instead, because it has less qubit overhead. And also, they were not using the shells around defect clusters, so that also might be a reason why the super stabilizers are not performing as well as it should. So we did our own version of this, focusing on the physical error rate that's around 10 to the -3. And we are showing this plot, both axes of this plot in the log scale. So we actually found that the defective patches generally have higher fidelity than the defect-free patches of the same code distance, which is the opposite of what they found. And then, so to estimate the performance of the defective patches, so that seems to naturally require you to pick a physical error rate, but we don't want to stick to a single value, so instead we feel that the slope of these log-log plots might be a good indicator to take, because it's just one single value, but it characterizes the performance of code like just like in a whole regime below this physical error rate of like 2 times 10 to the negative 3. Yeah, and if you look at the plot of the logical error rate of a defect-free patch, you will see that, well, like it's going to be a straight line when your physical error rate is low enough, and we see the same for the defective patches. So we found that actually code distance is a pretty good indicator of the performance of the defective patches. So we were sampling a bunch of like random defect distributions, and then see the code distance that it results in, and then we plot the slope that I mentioned before against the code distance, and we found that, yeah, like although there is some variance, the code distance is a pretty good indicator. But then we also wonder whether it's possible to find a second indicator that could help us explain the variance. And it turns out that we can do a combinatorial argument. If we look at the number of unique shortest logical operators in a patch, it could be a pretty good second indicator that gives more structure to the scatter plot. And it also helps explain why the defective patches generally perform better than the defect-free patches of the same code distance. That's because the defect-free patches usually has higher symmetry. And let me explain a little bit more. Here I'm showing a picture of a defective patch that's from a previous slide. You can see that if you want to find the path between the two red boundary that has the shortest length, then actually you don't have that many options. You have to go to the middle when it's like the thinnest. But for a regular square, there are way more options where the logical error could occur. So yeah, it's a very natural thing from the hindsight. Yeah, but like just to show that like it wasn't natural to us at first, I'm gonna show some of the less effective indicators. So one thing that we try is to look at the proportion of disabled qubits. And it doesn't really give us more information beyond the code distance already tells us. And then, so another thing that we try to look at is the diameter of the cluster. So we were wondering whether having large clusters would make a code perform worse. But then we found out that looking at the diameter of the cluster, again, doesn't tell us more information than what the code distance already tells us. So this shows that the shells are already doing pretty well to protect us against the larger defect clusters. So now we can move on to another goal of our work, which is to estimate the resource overhead that's due to defects and to see what are the design choices or like error model that potentially affect it. So for this setup, we imagine that each triplet holds one logical qubit, and then we define the yield to be the proportion of triplets that can hold a logical qubit that's at least as good as a defect-free one with a certain code distance. So that means to tolerate the defects, the triplet width should be larger than the target code distance. And if you have those two values being the same, then that means you have no tolerance for the defects, and that's the baseline case where you cannot use the super stabilizers. And we have two defect models, one with only defects on the links, and the other one, we assume that the qubits and the links are broken at the same rate. And the physical motivation for having both qubit and link defects is for the tunable transmons. I was told that the links and qubits for tunable transmons are roughly as complicated as each other, so they might have a similar chance of being broken. And the model where we have defective links only is just a simplified understanding of the frequency collisions. We assume that you can, when you have a defective link, you can disable either end of it. So here are some results for the yield and the factor of qubit overhead. And in this case, we only have defective links. And we define the resource overhead to be the average cost in terms of the number of physical qubits divided per logical qubit and scaled by the ideal case in which you have no defects at all. And we can see that the baseline with no tolerance of defect, it quickly drops as you increase the defect rate. But as you make the triplet larger and use the super stabilizers, it drops much slower. And on the right-hand side, I'm showing the factor of resource overhead. The takeaway is a different defect rate. It makes sense to use a different size of the triplet to have different level of tolerance to defects. But at the same time, using a larger triplet also means you have to have more physical qubits on each of them. So there's a trade-off. So it's important to reach a balance between them. And so. And if we take the minimum of all these lines at each point, we get a curve that shows the factor of resource overhead that you can reach with the approach of having super stabilizers on triplets. And we did the same thing with the other arrow model with defective links and qubits. Of course, we get lower yield and higher overhead because now there are more defects. Another reason is qubit defects could lead to lost syndrome qubit half of the time, and it creates more damage to the code than the broken data qubits. So we thought about ways to mitigate this. Well, you can either do it by somehow improving the protocol for adapting the surface code, but we thought of another approach, is if you just translate your surface code patch by 1 in both the vertical and horizontal direction, you can essentially swap the assignment of the data and syndrome qubits. And if we don't want to do this, we can also design the triplet in a way such that if you rotate it by 180 degrees, the data and syndrome qubits are swapped. So assuming that we can do this, we ran another set of experiments to see if this actually improves the yield in the presence of both defective qubits and links. And it turns out that you do get a significant improvement in this case. So yeah, so that's a design choice to be considered. So here is the factor of resource overhead for different target code distances, because we want to see if this overhead is higher when we aim at a larger code distance. And it turns out that this factor of overhead doesn't actually depend strongly on the target code distance. So we were wondering whether for larger code distances we need to distribute the logical qubit on multiple triplets, but from these results it seems that it's not strictly necessary. And for both of the arrow models that we were using, like the resource overhead under a reasonable assumption of defect rate, it's always a small constant number, which is like, I wouldn't say it's not expensive, but like it's just not as expensive as like the exponential curve that you will get without modularity or without any tolerance to defects at all. But there is a complication that I didn't explain in previous slides, which is if you don't position your chiplets carefully, then this situation might occur. Like you have two logical qubits side by side. If you look at them on their own, the codistance only decreased by 1 due to the defects in the middle. Like the codistance in the horizontal direction, it drops by 1. However, if you imagine that these two are merged and a lattice surgery operation along the middle line, then actually you're able to like go from the top to the bottom and skipping all these areas, so the codistance drops by more than half. And we actually, we definitely don't want to run into this situation when we like run an application. So yeah, we need to. So when building a modular device with defective chiplets, we need to arrange the chiplets well to avoid this situation. So we ran some simulations to verify that avoiding this wouldn't significantly lower the yield. And we did this by placing some constraints on the boundary. Well, if we disallow any deformation on the boundary, or essentially any defects on the boundary, that does change the yield. But if we just make sure that like the size of the deformation on the boundary wouldn't like lower the codistance, then yeah, like we found that the yield wouldn't change much. So I actually haven't really talked about the disadvantage of the monolithic architecture, because like what if we use the super stabilizer but have a huge monolithic device underlying it? Like wouldn't that also be wise for some situations? Well, so it turns out that the disadvantage of doing that is that some regions of the device would not be able to support logical qubits that meet whatever your standard is. And a quick back off the envelope calculation can show that these suboptimal regions can actually significantly increase the program infidelity. And when you don't use those regions, then you essentially lose some of your device connectivity on the logical level. So you don't want to do that either. And also you don't get to arrange the triplets to avoid the situation that I talked about on the previous slide. And here I'm showing like the distribution of the codistance of defective triplets with 33. And so what I showed in blue is what I imagine to be like the triplets that you don't want to use. That would be thrown away if you have a modular device. But if you have a monolithic device, you have no choice but to include them in your device. And it turns out that, well, this might not seem to be a significant proportion, but they can actually lower your program fidelity by a lot. And here is a summary of the project. So we found that the surface codes adapted to defective patches, they actually behave similarly as the defect-free ones in the sense that you can characterize their performance with the same indicators. And we also found that modular architecture combined with the super stabilizers can help reduce the resource overhead of surface code that's due to defects. But it's still important to reduce the defect rate to avoid wasting the good qubits. And we also found that the freedom to reassign data and syndrome qubits could improve the yield when there are qubit defects. And we also note that the arrangement of the triplets could affect the fidelity of interaction between the logical qubits that are supported on them. And finally, we recall what we showed at the beginning, which is the stability experiment could help us identify cutoffs for not using a certain bad qubit or a link. And I also have some possible topics for discussion, which is how does fabrication errors affect other codes? So I imagine that you can consider QLDPC codes. I mean, they do have some redundancy in their checks, so I'm not sure how much their performance is affected when you have one broken link. And the FlowCAD code could also be interesting. There's actually a paper that talks about defects on the FlowCAD code, but I haven't read it yet, so I'm wondering if anybody has read it. And also the codes on the heavy hexagonal lattices. Yeah. So, yeah.
Questions?
Okay.
I think you were doing your experiment, your numerics on single logical qubit per chiplet. And I understand the argument against doing a whole monolithic thing, but it seems like there might be a trade-off for doing a few logical qubits on chiplets, depending on the defect rate and things like that. Have you looked at that and you have a sense for what that trade-off would be?
You mean supporting multiple logical qubits on a single triplet or the other way?
Yeah, logical qubits.
Yeah, so the thing about that approach is that it has less flexibility. Okay.
Right, I understand
Yep.
your argument for a large monolithic one.
Right.
But are there regions where it would be good to say have 4 logical qubits instead of 1 logical qubit on a chiplet?
I think, well, we actually didn't do that study because that requires assumptions on how the interchip links compare to the on-chip links, and also the mechanism of fabrication errors. For example, like if you are considering fixed frequency transmons, then like if you already know the qubit frequencies that are along the boundary, you can imagine which 2 triplets can go well, can be combined, and which 2 may not be combined. For other models of defects, then like you may create additional broken links that are not that you cannot predict in advance when you combine 2 triplets. So it's like different, and we didn't really want to make too many assumptions on the source of the defects, so we didn't do that study. But yeah, but if you have a particular type of hardware in mind, then I think that study could be done and could be useful.
Thank you.
So thanks very much. I think it's really great to see this kind of thinking about yield worked out. I'm just wondering about the problem of sort of reliability. So I would imagine that as you operate the computer, some of your qubits are just going to die. And then that's going to require potentially the same kinds of strategies, but with less flexibility because you don't get to place the triplet. So I'm just wondering if you've thought at all about that kind of setting where things sort of switch off and you would have to make decisions about how long you would work around for a while and then disable a logical qubit or something. I don't know. Anyway.
Yeah. So you mentioned that you could disable a whole logical qubit in response to like a sudden disruption. I think for some type of errors that might make sense. For example, if you have cosmic rays that affect a large group of qubits, then it might make sense to totally disable one. If you have 1 qubit or a few qubits that are broken, it might make more sense to just adapt the code on the spot and then and then deal with it. There's actually a paper that was out at a similar time as ours that put more of an emphasis on that kind of dynamic defects. So essentially the way that you do it is that you keep track of the syndromes that are ones when you do your quantum error correction. If you see too many ones in a short period of time, I think what they recommend is to check over 6 rounds. If you see more than 3 instances of ones, then you say that this qubit is bad, and you just dynamically create a super stabilizer around it on the spot to protect your information. So that's what they recommend.
Thanks.
So can you go back a few slides?
Sure.
When you're looking at the trade-off between the error rate on the x-axis and different distance curves? Maybe a couple more, I think. Yeah, that one.
Yep.
Actually, the one before that.
Yep.
I think this is one. So there it looks like you're fixing the distance, is that right?
I'm fixing the target code distance,
Yeah.
but I'm varying the chiplet that I imagine would hold the logical qubit, which is characterized by the symbol L.
Right. So like in an actual practical sort of setting, what you really want is to fix the logical error rate, which depends not just on the distance, but also on the physical error rates as well. So you thought about cutting the data in a slightly different way, which is fabrication error rate and Pauli error rates, for example, on the logical.
So that's actually related to a point that I made before. So I'm actually using the code distance as an indicator, and actually what I put on the axis is a simplified version of what I was doing. So what I actually mean by code distance there is I want the defective patch to perform as well as the defect-free patch of the given code distance. So it's there's actually a logical error rate behind this. Hi.
Thank you for the nice talk. So you mentioned we had a bit of a talk that there's a difference in performance depending on whether you choose to measure these super stabilizers 1 time or 3 times or something like that.
Yep.
Does that change depending on the pattern of defects and what system do you choose for your analysis?
So I believe you're talking about the shells around defect clusters, and so we want to. We definitely want to know how many rounds do we need to measure the X gauges before we switch to the Z gauges and vice versa. So this paper that I mentioned at the bottom, so it recommends that the number of rounds that you do the measurement before switching should be proportional to the diameter of the cluster, and in our simulations, we just set it to be the same as the diameter of the cluster, and it works pretty well.
Sorry, the diameter of the cluster, you just mean the size of the shell?
Yes, for this example, I think we counted as having diameter 2, yeah. And if you have a larger one, you just alternate between the X and Z even less frequently.
Maybe a follow-up question. Would that make a difference when, say, you have defects at the boundaries of the chiplets and you are usually measuring them a different number of times? And you try to perform that slightly different.
Sorry, I didn't hear that question very well.
Sure. Sorry. Will that make a difference if you have defects on the boundaries of 2 chiplets and you're originally using a different measurement schedule, but now you have to use a new measurement schedule to perform that?
So when we have a defect on the boundary, it actually doesn't affect the measurement schedule very much because you just have a, yeah, I mean because because we just delete that qubit and oftentimes some surrounding qubits from the code. So we're like no longer considering them at all. Yeah.
But when you're doing this, you're also comparing it to ones that have got defects in the middle.
Yeah.
And so this could have the original measurement schedule, but the ones in the middle would have this different measurement schedule.
Mm-hmm.
So if you run this under the sort of, I don't know.
So yeah, what we found is that, like, at least in the regime that we study, yeah, like we just need to use the code distance and the combinatorial argument to assess the performance of the code. It doesn't really depend on like how many deformations you have on the edge versus versus whether if most of your defective qubits are in the interior. Yeah, these are things that we thought about at the beginning, that we wonder whether there should be a difference, but then at the end, it's just very simple. It almost looks like we did this all in, all in vain. But like, but this is what often happens. You just arrive at a simple conclusion that was now obvious at the beginning.
Yeah. No more questions? I think we're actually on time, so let's thank everyone.